All right, good evening. How you guys?
Good.
So let me set up this slides. I'm getting feedback, so let me. Are you guys getting feedback or is it just me?
I'm not getting anything.
Ah, I see. I have a preview window open. All right. So today, yesterday, we talked about GPIO and how to use it in PLP CPU. The midterm is still October 1st, Wednesday. We'll do a review session next Monday, so please go over the concept list and see what you want to ask or go over in Monday, and we'll have our midterm the Wednesday of that week. So last time we talked about parallel, right? So we talked about how in parallel communication you have multiple data wires, and for serial you have one data wire per direction. So with the parallel, the hardware is simpler than serial because let's say you have an 8 bit parallel communication channel. So you just output the byte to your I/O pins, and that's it. You just transfer 8 bytes. There's some synchronization, which we'll talk about later. But with serial, even each bit, you will need some timing to be able to, in this example, to be able to transmit 1 byte. So serial communication will have more complex hardware, not in terms of the number of wires, uh, just in terms of like the uh, the the timing of it. So we saw some of the devices. So before we dive into serial communication, let's talk about the difference between synchronous versus asynchronous communication between two devices or two nodes. So what do you think synchronous means?
Synchronized to a clock.
So synchronous clock. So we haven't really talked about clock before. So what is a clock?
Timer of operations.
Kinda. Right. So I think the clock is a bit of a misnomer in
Mm-hmm.
some cases when you do a synchronous communication because it doesn't have to be a clock. It doesn't have to be a regular signal. Right? But you're right. There needs to be a synchronizing signal between the two ends of the communication channel. Right? So there is no need for predetermined speed, most likely, because you can have one end, usually called the master of the channel, that will drive how quickly the data will get transferred over to the slave device. So the slave device will wait for the synchronizing signal to actually do the communication. Is that clear?
Yes.
So for asynchronous, there is no synchronizing signal, probably other than a bit of the packet that says, I go. So after the transmitter sent this bit of information, both ends will need to know how to handle what comes right after. Right? So when the transmitter says, here I go, let's say I'm sending you 8 bits, you better know how quickly I'm sending these bits to you. Right? So there is a predetermined data rate that both ends will need to be configured to talk at before communication can occur. Otherwise, either end will see garbage. Right? Because the transmitter may be going twice as fast as the receiver, and you'll just receive nothing, basically.
Mm-hmm.
So this is a parallel, synchronized parallel, just an example. So you saw this 8 bits of signal lines where you can actually send a byte at one time. So to make this communication synchronized, you will need, for example, this signal, the data valid signal. So the receiver will wait for this data valid signal to be asserted. So when this data valid signal is asserted, it knows, hey, this data is good, sample it. Of course, there's other things that you have to think about, like how long can the data valid be, right? You have to know like how long the receiver needs time to sample that data. So there are some timing details that you have to work out between the two ends, but that's it. You just have a signal that says, okay, this data is valid, sample it now. After a certain amount of setup time, hold time, which we'll talk about later, then the receiver can actually read that value off the channel. So it takes an extra physical wire for synchronization. So is this clear?
Yes.
So far, so good. So what about synchronous serial transmission? So this is what Stacy said earlier about the clock signal. So it could look like a clock signal. So basically, this is the same byte of data that is being sent from the transmitter to the receiver. So what the synchronizing signal does, in this case, it could be a clock. All right, the transmitter will assert a value in the data channel, and then when it's done doing that for that one bit, it will flip the clock signal low to say to the receiver, hey, I have this bit of data that is valid, sample it. And then, of course, the transmitter, like in parallel case, it has to wait a certain amount of time to make sure that the receiver gets that data, and then go to the next bit and on and on. So an example of this kind of channel is the SSI. I think it's called the synchronized serial interface. The SPI, the serial peripheral interface, or the I2C or I2C. So these are really common, especially SPI and I2C are really common ways for a microcontroller to talk with other devices on your system. Right. So you have a data line and you have a clock line. So for SPI at least, you can have another signal that selects which device the master node is talking to, right? So you can have more than 2 communication channels just to synchronize who you are talking with, which we'll talk about in a few weeks, and just explore it. With I2C, it's even more interesting because you only have two wires, and you can have more than 2 nodes speaking in with each other. So there are these things that that people use to be able to talk with other devices from your controller. That's good?
Mm-hmm.
Jason, you have a question?
Nope.
All right. So with this kind of transmission, with the synchronous transmission, the receiver device is simpler because it'll just wait for the clock or the synchronizing signal to do anything. Right, so it won't do anything until it's told to do something. So, from the hardware standpoint, this is less complex than if you do it asynchronously, which we'll see here. Right, so this is an asynchronous serial transmission. So, like I said before, we have the start bit that denotes the start of the transmission, and basically the transmitter said, "Here I go. You better sample the rest of the things I'm sending you." So when the receiver sees the start bit, in this example, when the signal line gets pulled low, that's how it knows that, hey, I better start sampling the next 8 bits if this is a 1 byte channel. Does that make sense?
Yes.
So the transmitter and receiver must be configured to talk at the same rate and with the same configuration. So transmitter, if it's sending 8 bits per packet at certain rate, the receiver must be doing the same thing. It needs to be expecting 8 bits of data per packet at the same rate. Otherwise, what would happen? What would happen?
Your data would be corrupt.
corrupted. It will be a garbage.
Yes.
Right? So there is a margin where you can vary a little bit, but if it's too much, then you will not be able to communicate. Right? What's worse, you think you're communicating, but you're off in a bit, slightly off, that you only get errors once in a while. That's even worse, right? So you want to make sure that both sides are talking at the same with the same rate and the same configuration of packets. So what's the advantage of a synchronous serial transmission? You don't need an extra line to synchronize, or just one wire, one direction, aside from reference or ground, and then go. But the disadvantage would be what? What would be the disadvantage of doing this asynchronously compared to synchronous channel?
I mean, you need two configurations on each end, right? So you got to make sure two pieces of equipment are set up.
So what does that imply about both equipments? They are more what? At least in the receiving side, it has to be more what? More complex. Right? So now it has to worry about timing and sampling the signal to make sure that it's sampling it correctly. As opposed to in synchronously, it doesn't have to do that. You just look at the synchronizing signal. Oh, okay, I have to sample this bit. All right, next bit, etc. Is it clear?
Yeah.
Yes.
This way, when the receiver sees the start bit, it goes like, oh, wait a second. Now I have to time myself so I can sample the next 8 bits. So that necessitates the receiver hardware to be more complex to be able to do that. Is that clear?
Yes.
Yeah.
So now that we know the difference between synchronous and asynchronous communication, parallel or serial, so the most common synchronous communication channel that people have been using are the UART. So it stands for Universal Asynchronous Receiver/Transmitter. So this has been used for a long time, like at least the protocol. The physical layer could be different. UART can run at various voltage levels, but the general idea, the idea is the same on how to actually format your packet and how things get sent and everything. So it is asynchronous. So for example, if you want to connect your controller with a device that can talk UART one way, all you need is the one signal line and your reference. If you want to go both ways, then you need 2 signal lines. It's full duplex. So usually it's full duplex. So what it means, you have 2-way independent communication channel. So you can transmit while receiving, and the CPU the controller usually can handle this. So it's along with SPI and I2C are the most common onboard serial communication. So what's different between UART and SPI and I2C? What differentiates UART with the other two? Hint: those two have a clocked signal.
Okay, so there's the other two are synchronous.
Yes. Right. So with SPI and I2C, you have this notion of a master and a slave device, right? In UART, not necessarily. Both devices are independently keeping track of the data rate. Does that make sense?
Yeah.
Yes.
So UART has an active low. Usually, this is not universal, but usually it's active low, right? So when the line is idle, it's 5 volts or high voltage, and when you send a start bit, it gets pulled low for 1 bit of whatever data rate you're going for, and then it starts transmitting the data. So if the bit is 1, it stays as low. If the bit is 0, it gets pulled high. So PLP CPU has this module, has this device so the PLP CPU can talk with other devices that can also do UART. So PLP-CPU does not have SPI and I2C, but it does have UART. So before we dive into the PLP-CPU UART, let's look at the communication rate. What do you think the communication rate is? Like, how do you define the communication rate?
Bits per second.
Bits per second. Right, so it's how fast you can you push bits to the communication channel. It's called the bit rate. Usually UART packet. This is, note the word usually. So this is by no means universal, but usually UART packet is comprised of one start bit, 8 bits of data, and one stop bit with no parity. So the shorthand for this configuration of a UART packet is called the 8N1. So basically you have 10 bits per packet, of which 8 are useful data. Does it make sense?
Yeah.
This is not always true. There are UARTs with less than 8 bits of data per packet, or with parity. Parity is used to actually do error checking to see if your packet gets received correctly. But the most usual UART configuration nowadays is 8N1. So, but you have to know that it's not universal. So when you work after this and then you encounter legacy systems, you have to be careful and make sure that your UART is configured correctly to talk to that device. So usually microcontrollers documentation talk about this rate in terms of baud. This harkens back to the modem days and dial-up where they use baud. So baud is basically symbols per second. So baud rate is the term baud rate, the phrase baud rate is redundant because baud already means a rate. So if you use bit as your base of symbol, then 9600 baud just means you have a bit rate of 9600 bits per second. And if you use the 8N1 configuration for the UART, then your effective data rate is 960 bytes per second, right? Because that's how many useful bytes you get per second when you have that kind of data rate, bit rate. Does it make sense?
Yes.
If I set up my UART to talk at 200 kilobaud, what is your effective data rate? With 8N1 configuration.
20,000.
20 kilobytes per second. Cool?
Mm-hmm.
So now we're going to talk about memory map UART on PLP CPU. So how do you think UART is configured? The UART module is configured in PLP CPU. How many registers do you think it needs? Take a guess. Pick a number.
Oh, I'm sorry. I had to take my headphone off for 1 second. Can you repeat that?
How many registers do you think the UART needs to expose its interface to the programmer?
$10.
Sure, right? But you're wrong.
Yeah. I said yes. I guess.
You can when you design your own CPU and have 10, right? So these are the 4 registers that expose the UART engine to the programmer, right? So at this point, now you should have a good feel of what memory map I/O is, right? So basically, it abstracts away the physical layer from you and have these registers with where each bit means something, and when you write or read from it, it manifests on the physical layer. Does that make sense?
Mm-hmm.
This is common for many microcontrollers. Right? Usually you have command register, status register, receive buffer, send buffer. In many controllers, the command and status registers are combined. Right? So we split it up so it's clear what the distinction is between the command register and the status register. But in many controllers, they are the same, and it could be confusing when you try to interface with this I/O device, which is the UART. Right, so this module is connected to the data bus, and these are the registers and the addresses that are used. So it starts at the base address for this module in PLP CPU is this. So it's a F0, A0, 4 zeros. So as you see here, the top 3 bytes of each register are unused, right? And I think it always returns 0 if you try to read from it. And the bottom byte, even the bottom byte for the command SS registers, only 2 bits are used, right? And then you have the receive and send buffer where the whole byte is used. Basically, like intuitively, you should be able to see like what these 2 registers do, right? Can you give me a guess of, for example, what the receive register is used for?
Would that be your data bits?
Data bits that came from
The other
end of the channel.
right.
Right. What about the send buffer? Jason? What do you think the send buffer is used for in the UART device? Jason, are you here?
Yeah, I'm thinking.
There's a full duplex device. It can transmit and it can receive. Stacy said the receive buffer, well, if I'm receiving something, I need somewhere to hold the data before I use it, right? What about the send buffer? What do you think it does?
Holds the data we're about to send?
Yes, correct. Now, what's missing? Now the thing that we have to think about is like, so how do we actually make it send, or how do we actually make it receive, and how do we know if we can send, and how do we know if there is data in the receive buffer? Now you can make the connection to these 2 other registers. Like what possibly could they do with this device, right? Can you give me a guess of what the command register does?
Which said if it's to receive or send, wouldn't it?
Well, to send and to tell the UART, hey, I got the data, you can receive again, right? What about the status? It tells us what? Well, same thing. Well, similar. It tells us, hey, I have data, or hey, you can't send yet because I'm sending something from before, right? So you don't want to clobber your send buffer while the UART device is sending something out, right? So you have to check for that. Is that clear?
Yes.
So the command register, status register are really like common things that you will encounter when you try to program microcontroller. So they'll throw these terminologies around, like this is status register for this device, this is status register for this part of the CPU, which just means that each bit of the register means something of the state of the CPU. So the command register is write only. So when you do a store word of 1 to the command register, it tells the UART device to initiate a send, a transmission. If you write the number 2 to the command register, it clears the receive ready flag, so the UART device now can receive again. The status register, or the bit 0, is the clear to send signal. So when this signal is set, then the UART device is idle, and the transmit is idle, and you can actually do a send command by writing 1 to the command register. When you're trying to read, you want to check for this bit 1 to see if there's new data, right? If it is, it will be set. Then you can load it from the received buffer, and then write a 2 to the command register to clear it. So the UART will what? What do you need to clear the ready flag after you take the data off the buffer? No guesses? You got your data. Why did you have to clear the flag? Because that's how you let the CPU know that the data has been loaded, and you can clobber that for the next one. Like you can use the receive buffer for the next incoming data. Does that make sense?
Okay. Yeah.
So in some microcontrollers, the act of loading the data from the receive buffer to your CPU register clears the flag. Right? By doing a load from the receive buffer, you're telling the, not in the PLP CPU, but in other CPUs, when you load from the receive buffer, it tells the UART, hey, I've got this data. And then you can receive again. But in PLP CPU, no, you have to explicitly write a 2 into the command register to clear that flag. Does that make sense?
Yes.
Also, in other architectures, these two can be combined. Right? It's not necessarily a different register. It could be the same register. So you have to read your datasheet and see and make sure you know how to use their I/O modules and how to interface with them. Right. So sending data, first you check the status register for the clear to send signal bit 0. If it's not clear to send, which is if the CTS signal is clear, do not do anything. Right. Otherwise, you'll mess with the whatever the UART is currently transmitting. If CTS is set, which means the UART is ready to send, then you can write the data you want to send to the send buffer. After you've done that, then you write the value 1 to the command register to actually make the UART device send the data out. So I have this animation. So now, let's say this is your status register in the bottom here, and you're trying to send a byte of data. You can't right now. Why? At this point, why can you not?
CTS set?
Yeah, CTS is not set right now.
Yes.
So you're not clear to send.
Right.
So we can have a loop and check for this bit until it clears up, until it gets set. Boom! Now it's set. All right. So now we can fill the send buffer with our data. So we do a store word of our data to the send buffer. Now, what do we do next? We write 1 to the command register. After that, after we've done that, then the UART will clear the CTS, right? This signifies that, hey, I'm sending, don't mess with the send buffer right now. So it will start sending the start bit and push the send buffer out to the transmission line. Does that make sense?
Yeah.
Mm-hmm.
So the UART actually uses a shift register, and it clocks the send buffer out. So the least significant bit gets sent first. After it's done, send buffer is empty. It's done sending the stop bit, and clear to send is set again. Then you can transmit the next one. Is that clear?
Yep.
Yes.
Is the flow chart forming in your mind on how to do this programmatically in PLP CPU?
Yeah, that slide helps.
The what?
That last slide brings it all together, I think.
Yeah, so you just have to check for CTS and make sure you don't send while CTS is cleared. Right. So what about receiving? So you check the status register for data ready, all right, signal bit 1. If ready is set, then it means that whatever is in the receive buffer has valid data. So after you load it from the receive buffer, then you can write the value 2 to the command register to clear the ready bit, so the UART can receive data again. Otherwise, it'll ignore any incoming data if you don't write 2 to the command register. So let's look at this, right? So on the status register, ready is not set. So if you try to load data from the receive buffer, what would you get?
Just garbage.
Garbage, right? It will let you. There's nothing stopping you. You can load words from anywhere, and CPU will just say, okay, fine, right? But it will contain nothing. Well, not nothing. It will contain garbage. You don't know what that byte is, right? So when the UART device sees a signal, like when it sees the start bit, it starts shifting in data until the receive buffer is full. When you get full data, then it sets the ready flag, which means that your receive buffer has valid data. So at this point, you can load this data to your register to be computed, and then you write 02 to the ready command register, which means, hey, now you can receive again. Is that clear?
Yeah.
Yes.
Easy enough, right?
Yeah.
So let's try it out in PLP tool. Can you see the window?
Yep.
Yes.
I think that one was fine. So I'm on a wired connection, so it should be better. How does my voice sound?
It's fine.
Awesome. So, UART. What was the base address for the UART? You said
0F3. There was the 4. I don't know.
So,
hit F1. I'll tell you.
what? I think that's correct, right? So there's a trick. Like if you do a load upper immediate, also load immediate with the PLP CPU assembler, it breaks it down into 2 instructions, right? So if you use load upper immediate, it'll just load this to the top 2 bytes of S0 and fill the rest with zeros. So it does the same thing if you have done something like this. You just save 1 instruction. So when you program in assembly, then sometimes you start thinking about ways on how to optimize your program. Right? For example, if you run this, so let's say what will happen to S0. So if you execute this instruction, you see the bottom 4 hex digits are all 0. So you just save 1 instruction to load that address to your S0. Just a little trick, which is probably only true in PLP CPU or MIPS. But anyways, now what do you want me to do? Let's send Wira to the UART terminal. Right, so basically what we're trying to do here, we're connecting the PLP CPU UART to a desktop computer, for example, right, to a terminal. And we're trying to send those 4 characters to the terminal. That make sense? Should we do this?
Mm-hmm.
Yep.
So what's the first thing we do? Oops. Save this to save register so we don't clobber it. So what's the first thing you have to check before you try to send?
The
Command bit.
No, the status bit, but which bit? What do we need to
clear to
clear the
clear to
send?
send.
Right, so the 4 here offsets this address by 4, so you get the status register. Now, we are only interested in the first bit, so what do we need to do?
Mask.
We need to have a mask, right? So basically, this, right? This is the mask for the CDS bit. So we don't care about the rest. So we just mask it off with, well, not MD. It's 5. After this instruction, what should we have on T0?
You should have a 1 if it's clear to send, or a 0 if it's clear to send, and a 1 if it's not.
The other way around. You should get a 1 if you're good to go. You should get a 0 if it's not clear to send. All right?
Right, okay. Yeah.
So here we need to have a loop where you wait for the clear to send signal to be set. So when do we loop back?
If we get a 0, we loop back.
Okay. So see how nice masking is? Right? So at this point, the only possible value for T0 is what? 0 or?
1.
1. So that's why we have 0 register, because you compare against 0. It's a really, comparing against the number 0 is a really, really common operation. That's why the architects of the MIPS and the PLP CPU say like, hey, we just have a 0 register because it gets used a lot. Because otherwise you have to load 0 to a register. Right? So what this loop does, after you load the status register, and then you mask off the rest and get your CTS bit, if it's 0, that means you're not clear to send, and you keep on waiting. All right? So what if you are clear to send? What do you do next?
Then you can start sending your stuff.
And how do we do that?
You load it to the
Store it.
or store it to the send register.
So what address is store what? The first character, Wira, W, right?
Mm-hmm.
Mm-hmm.
So where's the send buffer? What's the address for the send?
Was it 4? Was it 8? So 8 offset.
Is it 8?
I don't know. I can't remember. That was like 2 slides back.
Oh, it's C. Right, so send register is C. So we offset by either C, we can do this, or it's 12. All right, so cool. Now we have the send buffer, W character. What's next? How do you actually initiate the transmission?
Go back to let me see that slide.
So you write 1 to initiate send. Oh, look at this. Our mask already contains the number 1, right? So by design, so you can send the mask to the what register?
To the command register.
Which is the first one. Oh! Now let's do a Raymond loop and see if this works. It assembles. So this button will show you the UART terminal. So this is like simulating where you hook up your PLP CPU to a desktop computer that can talk to UART, right? So what we expect to see here is that after we run this simulation, we should be able to see the character W here, because we're loading the character W into S1. So what's character W in hex? So just to here, if we put W, hex is 57, right? So if we put 57 here, it will do the same thing because ASCII W means hex 57. So either way we should get the character W on the UART. Let's see. Let's run this. So get from status. Looks like we have an error. Oh, UART is at 00000. Sorry, I need to change my slides now. This is incorrect. Alright, class. The UART address is F00000, not F0A0. So I'll fix the slides later. Sorry about that. So now we load from status, and since on simulation, like it sends the data instantaneously, so CTS will always be set on simulation. But in real hardware, you have to check it like this. So now we have the send buffer into. Boom. This is small, but you can see the letter W on the UART. Cool?
Yep.
Now let's send the whole thing. You cannot have duplicate labels, so now you send I here, send R here. Here we are sending the last letter of my name, A. 4. So I'm just iterating through these characters. Hopefully this will work. W, I, R, A. See, we've just sent my name to the other end of the channel. And that's transmitting in UART. Any question?
Nope.
Sounds simple enough, right?
Yeah, I'm gonna need a cheat sheet though to remember all the.
So you will always have a cheat sheet.
Status register.
Yeah, that's why usually like a controller and microcontroller manufacturers have the data sheet and have like reference sheets, so you can have like so when you program in C, even like the registers are named for you, so you don't have to remember the addresses. So that's it. Well, even in the midterm, I won't make you remember all these because it's pointless. I mean, in terms of like the.
But we're gonna need them all for the lab or the next lab, I'm assuming, right? So.
Oh well, we have the library for that, so you don't even have to remember all this. Yeah, we'll start using the PLP library on how to use them.
Cool.
So you just call functions and things like that.
Well, we did that once, right? Didn't we do it for the LEDs or the LEDs and the switches?
Yeah.
Yeah.
So if you look at the flowchart, here you load the status register, you mask off the rest, and just check for CTS, and wait until you are clear to send. All right. Just loop here until you're clear to send, and if you are, then you send out. You send the next character, third character, and the last character, and you stuck in the Raymond loop. Cool?
Yep.
So now, well, the point of this exercise is you, as the programmer, like from your perspective, the UART device are just a bunch of registers and bits that may mean something. All the bit flipping on the transmission line or the receive line you don't see that. All you see are bytes, status bits, and command words that you send to the command register. So that's usually how you interface with these kinds of devices. You don't actually drive the pins manually. You just have some abstraction in the form of registers. status and command registers and buffers that you work with as a programmer to make things happen. So this is very, very common in a lot of I/O devices. So make sure you understand the concept of memory mapped I/O and all the different special function registers. That's what they call it, SFRs. Any question?
Nope.
Stacy, I haven't heard from you for a while. Any question?
Are you gonna post this program here so we can reference to it?
So let's save it then. Just so I don't lose it. UART send. Now let's do a receive. What do you think? Hello?
Do what? You're gonna do a receive?
Do you want to?
Sure.
Or do you want to do it yourself? As an exercise? You have 5 minutes. I can
I think I got it.
I can already hear the other students when they watch this on YouTube. No, do it! Do it!
Okay. All right. Yeah. Let's do it for them who didn't show.
Now I want to torture them a little bit more. Should we do it? Stacy, should we vote?
Sure.
I can sense the sigh of relief from the rest of the students. Let's save a different one. You already received. All right, let's do a receive. So basically, on a receive, when we pull out this terminal, what we type here, you will get from on the receive buffer. In what representation, though?
In hex?
No.
Oh. In
ASCII.
what?
Yeah, because that's how terminals interact with humans. They're usually ASCII terminals. So when the user presses 5 on the keyboard, when it gets to your receive buffer in the UART, it will not have 5. It will have hex 35. Okay, let's do an exercise then, if you don't trust me. Now we have to change our mask to the ready mask, right, which is the second bit. Is that clear?
Yeah.
Yes.
So, similar, you load the status register, offset 4. You end it with our ready mask. Now, well, not end, I can. Now T0 should be either what? What are the two possible values of T0 after we mask it off?
0, no.
0 and?
1.
No. 0 and?
2.
2. Right, because we're looking at the second bit. If that bit happens to be set, when we mask the rest off, then we just get 2. If that bit happens to be cleared, then we just have 0. Alright? Now the meanings of the bit just means if it's 0, then the data is not ready. You get that? So if the status is 0, then you go back to ready wait and wait until you actually have data. Make sense?
Yes.
Well, let's move our Raman loop up here, so it loops forever and includes the receive. Now, if we get down here, that means we do have data. So what do we do now?
We load the buffer. What's in the buffer?
Where's our buffer?
Yeah. Was it 4? 8.
8. Yeah. So now we have our data on T1. So how do we make sure that the UART will receive again after this?
You have to clear the ready flag.
By writing to the command register, right? So this operation will write 2 to the command register, which will clear the ready flag. Like I said before, in other controllers, the act of loading from the buffer may clear the flag, but that's not universal behavior. So make sure you don't. Make sure you read your documentation when you do this.
Why would you not have that? Like just saying that you want to use that information more than once, I guess?
Yes. Or why KLP-CPU does not do that?
Yeah.
Just for clarity's sake.
Okay.
For the sake of clarity. Yeah.
All right, gotcha.
But now you fully understand like what's going on though, right? Why the ready flag is important to clear the ready flag.
Yeah.
Because that's the only way to tell the UI device, hey,
I'm good for some
I'm
more
good.
info.
Yeah. Okay. Now let's play with this. So see here, the processor is waiting on that ready bit to be set. Right? It's looping here. This is called polling. It's polling for that ready bit to be set, which tells you that there's data. Right now there's no data because we're not sending anything. So it just loops there checking for the ready bit. Is that clear?
Mm-hmm.
Mm-hmm.
Now in the UART, I'm going to type 5. You'll see that it'll fall through, load that 5 to T1, and then loop back. See that?
No.
Now, see what the hex value of the register is. It's not 5. It's 35.
That's what I said. I said it would be in hex. You said no, it would be in ASCII.
That's not clear. Hex is just a representation. You didn't tell me what the value is. The value is hex 35, which also means ASCII 5. This is a misconception that many students never shed, which is frustrating, right? Because it's just a representation. Does it make sense?
Yeah.
But do you see it though?
Yeah, but
I'm
I thought
Yeah.
what you were asking me was, what's this value going to be? What are we going to see? Well, we're going to see the hex value of it, even though the
you have
UART
to
is going
say
to be.
you have to say it's hex 35. You don't just hex value of it because it could be hex 5, and it's not clear.
Oh, okay. I see what you're saying. I got you.
Good. Do you really get it though? Because
Yeah,
that's
yeah, I do.
important. The
'Cause
distinction
I
is
would,
very important.
if I said hex, but it was just hex 5, it would be wrong. I got you.
It is completely wrong. Now I'm going to type capital A. See that? This is what Raymond said yesterday, 65, which is hex 41, which could also mean ASCII A. In our context, it's ASCII A because I typed it in the keyboard, all right, and that's how you interface with humans in terms of characters. You see that?
Yeah.
Now I'm going to do an @ sign. X40. Well, it's interesting. X25 percentage. So it's just a way to map those bit combinations to a character that we can read. That's it. That's what ASCII is. So let me repeat the question that I had yesterday in class. Like if I type 8, I get hex 38. Let's say we want to treat this as the value 8 that you want to use to compute with. So what do you do with this value in T1?
Subtract 30.
Or, I mean, that's correct. Or what else can you do?
You mask the top 7.
Mask off the top everywhere. You just end this with F, right? Just one F just to get the
Right.
bottom digit. So, how's your? Simple, right?
Mm-hmm.
Yeah, it's not that bad. I thought it was going to be pretty confusing at the beginning, but yeah, it's not that bad.
Not that bad. Why does it say I have one viewer, but I have 2 of you? So I'm not sure what's going on here. So now, do you have any other question?
Nope.
Anything about the midterm?
I haven't even started on that yet. Working
You
through
want?
the review anyway.
So I was going to do something cruel and start talking about midterm and stopping the broadcast. I thought it's going to be funny, but I don't think I'll do that because I
Or
can.
since only 2 of us showed up, maybe a couple of bonus points for me and Stacy, you know. It shows
Just for the
dedication that we're here.
Jason, just the
Yeah.
fulfillment that you get learning this like firsthand.
That's why that's why I showed up. Yeah.
Yeah. Now you know like all these different things, and you just got a Zen moment earlier with the ASCII representation, which you wouldn't have gotten if you skipped this. So learn for the sake of learning, man. No, I sound preachy. Looks like I have to stop now. So any final questions before I quit, and I'll see you guys next week.
No, I'm good.
I'm good too.
So now if I ask you to go through a datasheet for controller and tell me how the UART works for that controller, you should be able to do it, right?
Yep.
There's one thing that I didn't really touch. In PLP CPU, the baud rate is fixed. So in other controllers, you can change the baud rate. And so we cannot really talk about that until we talk about clocks in a couple of weeks. So, but in PLP CPU, the baud rate is fixed. That's not true for other controllers where you can change the data rate because you may want to talk to different devices that talk at different rates, right? So that's why you have that. Cool. If there's no more question, I'm going to end this lecture, and I'll see you all next Monday.
Sounds good. See you then.
Okay. See ya.
See ya. Good evening. Good night.